To do any repair properly, you need the right tools, and one tool no one should be without is a Haynes manual. They have over 200 titles available that contain information that's easy to understand. Haynes manuals contain photos and diagrams of a complete vehicle teardown that will easily help you become a better do-it-yourselfer. It's an easy way to save money and get that feeling of satisfaction that comes with doing the job yourself. Let the crew of professionals at Haynes help you on your next repair. Hi, I'm Bill Stern. Welcome to Car Care Seminar's videotape on emission system troubleshooting. You know, if you're like me, you like to work on your vehicle yourself. I do my own maintenance, like changing oil and filters, and replace whatever failed parts I can. That way I cut my driving costs, and I get the satisfaction of doing it myself. Now, as you know, today's vehicles are very complex, so you have to have more help. I get my help from the folks at Champion Auto. They give me the help I need by carrying the right products at the right prices and providing me with the right answers. Like the Car Care Seminar weekly TV show with helpful hints around the garage and repairs like the ones found on this tape. And remember, this tape is just one of the library of Car Care Seminar repair tapes, covering everything from basic maintenance to emission controls and computer repairs. It's all covered in easy-to-understand language using basic hand tools. Another right answer available at Champion Auto Stores are Haynes manuals. Haynes manuals are easy to understand and have illustrations and photos showing you everything from wiring diagrams to periodic vehicle maintenance charts, all on your specific vehicle. Everything you need to know about your car is in this manual. Now, the tape you're watching is designed to help you troubleshoot drivability problems caused by your vehicle's emission system. It will cover diagnosing and replacing many of the emission system components on your vehicle. Guiding us will be Scott Cusey, Champion Auto Store's Technical Communications Director. We hope by the end of this tape you'll be ready to perform repairs you may have thought you never would. Now, let's go to Scott.
When it comes to troubleshooting drivability or performance problems on today's high-tech vehicles, a lot of people figure that they can't work on them and they'll just have to take them into the shop. Well, that's certainly an option. In fact, I'd suggest you take it into a Crown Auto Service Center at your local Champion Auto store if you have to do that. But that's probably not the reason that you selected this tape. Because Car Care Seminar is designed to save you money by helping you learn how to perform the repairs on your own vehicle in a manner that will not only save you that money, but it'll help you do the repairs the right way and the safe way the first time and every time. Hi, I'm Scott Cusey, and I'll be your narrator and host as we take a look at troubleshooting drivability problems associated with some of the fuel and emission control devices on today's vehicles. Now, troubleshooting drivability problems used to be pretty easy and straightforward back when I started working on vehicles. Of course, that's when mechanical fuel pumps and carburetors and even point-type ignition systems were popular. But today's highly advanced and electronically controlled vehicles pose a new challenge for all of us. But it's not a challenge that we can't overcome. It just seems like the hardest part is either knowing where to get started or where to locate the information that you need to perform the task. As I just mentioned, this videotape will cover identifying and repairing drivability problems normally related to the fuel and emission systems. Now, during this chapter, I'll briefly discuss the topics that will be covered on this tape, as well as the tools that you will need to perform the repairs described. Now, beginning with Chapter 2, we'll move right into the emissions control system. The item we'll begin with is the A.I.R, or Air Injection Reactor Pump. Testing the air pump is what we'll cover first, and we'll continue that topic by demonstrating air pump replacement in Chapter 3, and air manifold and check valve testing and replacement in Chapter 4. In Chapter 5, we'll look at testing and replacing an item that has actually been used on vehicles for over 30 years, and that is thermal ported vacuum switches. Chapter 6 and 7 will discuss another system that's been around for quite a while, the E.G.R, or exhaust gas recirculation system. One of the key components for optimum performance and emissions control on today's computerized vehicles is the oxygen sensor. Chapters 8 and 9 will show you how easy it is to test the oxygen sensor, along with sharing some tips for successfully replacing one. An equally important sensor used on computerized vehicles for control of the fuel and emission systems is the coolant temperature sensor. Chapters 10 and 11 will discuss inspecting, testing, and replacing coolant temperature sensors. In Chapters 12 and 13, we'll be discussing how to test and replace idle air control motors, which are used to help control the air mixture and idle speed on fuel-injected vehicles. This item can definitely affect the emissions levels measured at idle. During our last chapter, we'll move down underneath the vehicle and discuss how to test and demonstrate how to replace your catalytic converter. They don't often fail, but when they do, it can be a tough one to figure out if you don't know where to look. Well, that pretty much wraps up the areas we'll be discussing on the tape. So now let's talk about the tools we'll be using to perform the testing and replacement portions of the tape. Now, everyone pretty much realizes you're going to have a pretty good selection of the basic hand tools to work on your vehicle. Now, some examples of that include combination wrenches, both metric and standard, a good selection of pliers, including locking pliers and needle nose type, quarter drive and 3/8 drive shallow and deep well socket sets, again, both metric and standard, a torque wrench, a hammer, some punches, and a rubber mallet, Phillips and flat blade screwdrivers, and one of my favorites, a magnetic screwdriver and a good selection of bits, safety glasses and a pair of work gloves, a handheld propane torch, a set of metric and standard tubing wrenches, a wire cutter and crimper, some shop towels and hand cleaner for cleaning up afterwards, a drain pan and some funnels, a soldering gun and rosin core solder, and a floor jack and a set of jack stands for any of the procedures that may take you down to the underside of the vehicle. Now, you'll also need a few basic shop-type chemicals and sealants like Teflon thread sealing tape, penetrating oil, anti-seize compound, and even spray carburetor cleaner. Now let's look at some of the more specialized tools that you might need. Torx bits are becoming a more popular type of fastener for many different items on vehicles all the time. So you'll most likely need a set of Torx bits that range from size 10 through about size 50. Now, another couple of common troubleshooting tools are these right here: a hand vacuum pump and a handheld vacuum pressure tester. We'll use these to check vacuum diaphragms and vacuum-related switches and relays. You'll also need to have a handheld digital volt-ohm meter for testing the electrical circuits. And it's also a good idea to have around a couple of jumper leads too. Now, here's a handy little item that many people don't even have, and that is an inspection mirror. It can really help you get in to see things in places that you've never thought you could see. Now, one of the most important items that any mechanic has is the correct service manual for the particular vehicle they're working on. Now, one of the best you can buy is a Haynes manual, because they deal specifically with the disassembly and reassembly of your particular vehicle. From specifications to detailed instructions and illustrations, you'll find just about everything that you need to know about your vehicle in one of these. And that pretty much wraps up our tool selection. Now, on the front cover of this tape, you'll find a troubleshooting guide that lists the most common drivability complaints that can be caused by one or more of the items that are discussed on the tape. Now, before you begin watching the tape, check this guide for the driving symptom that you're experiencing with your vehicle. It might save you some time. Also, right at the beginning, it contains a chapter listing and a space for you to enter your VCR counter number next to each chapter for fast and easy future reference. As you're viewing the tape, you'll also notice that we've included the chapter number in the lower right-hand corner of the screen. Now, one last thing I'd like to point out is that the demonstrations shown on this tape are typical examples of repair procedures being performed on common vehicles. Now, for details on the procedures for your particular make and model, once again, I suggest you pick up a Haynes manual before starting your repairs. And the best place to pick one up is, of course, Champion Auto Stores, as they carry a complete line of Haynes manuals right in stock. I'd like to thank you for choosing Car Care Seminar and for giving us the opportunity to help you learn more about your car. Before you start your next project, check to see if there's a Car Care Seminar tape to help you do the job the right way the first time. Now, let's get started with our first repair.
The A.I.R, or air pump, is the heart of the air injection reactor system, which plays a key role in lowering your vehicle's exhaust emissions and protecting our environment. The A.I.R system provides several different functions related to vehicle emissions. It reduces hydrocarbons, HC, carbon monoxide levels, CO, and helps to lower nitrogen oxides, or NOx emissions. It's also used to rapidly heat up the catalytic converter on engine startup so conversion of exhaust gases can occur sooner. An air pump is actually a belt-driven air compressor on the front of the engine that provides cool air to the A.I.R system. Air is drawn through the centrifugal filter fan at the front of the pump. It is then sent to a diverter valve that directs it to the air cleaner, the intake manifold, the exhaust manifolds, or the catalytic converter in different situations to help control exhaust emissions and drivability. When it is directed to the catalytic converter, it provides additional heat to help control NOx emissions. When it is directed to the exhaust manifolds, the oxygen in the air helps burn off excessive hydrocarbon and carbon monoxide gases before emitting them into our atmosphere. A failing air pump can often be detected by a loud squealing noise coming from the pump's drive belt. Many times the belt will only squeal for a short time before breaking and flying off while driving. This is a sign the pump is locked up and requires replacement. Oftentimes, a locked up air pump is due to a defective air pump check valve. It is the duty of the check valve to prevent hot exhaust gases from backing up into the diverter valve and pump. If the check valve fails, soon after the diverter valve and pump will also fail. Another sign of an inoperative A.I.R system is if you fail to pass a vehicle emissions inspection. Since the A.I.R system helps lower exhaust emissions, a failure in the pump will produce higher than normal levels of hydrocarbon and carbon monoxide gases. Begin any inspection of the A.I.R system by carefully checking all hose connections on the pump. Be sure they are not loose, leaking, or broken. Next, check the pump drive belt and belt adjustment. If the belt shows severe signs of slippage, wear, or cracks, replace the drive belt. Also, be sure to inspect the black centrifugal filter fan and clear it of any dirt or debris. To test the pump for proper operation, first allow the engine to reach normal operating temperature. Locate the output hose from the pump and squeeze the hose with your hand as the engine is running. Next, gradually increase the engine speed to around 1500 RPMs. You should feel an increase in the number of air pulses inside the hose as engine RPM is increased. If a change in air pulses is felt, the pump is functioning properly. If no pulses are felt, the pump is defective and must be replaced. Another way to check the pump is to remove the output hose from the pump, start the engine, and feel for any air pulses coming from the pump or output hose. If no pulses are felt, replace the pump.
Now let's briefly review the steps necessary to identify a faulty A.I.R pump. First, visually inspect the A.I.R pump drive belt. A broken or missing belt is usually a sign of a locked up pump. If the pump is locked up, be sure to inspect the check valve and diverter valve for failure also. Next, inspect all the hose connections on the pump. Make sure they're not loose, leaking, or broken. Also inspect the centrifugal fan and clear it of any dirt or debris. To test the pump, start and run the engine until it is at operating temperature. Squeeze the output hose and raise the engine speed to 1500 RPMs. You should be able to feel an increase in the air pulses inside the hose. If no pulses are felt, replace the pump.
The items you will need to replace an air injection reactor or air pump include a 3/8 drive socket set, a standard and metric wrench set, a rubber mallet, some thread lock adhesive, a set of screwdrivers, a torque wrench, and the correct replacement air pump and check valve for your particular vehicle. Whenever installing an air pump, we recommend replacing the air pump check valve at the same time. Most air pump failures are caused by a defective air pump check valve. If you install a new air pump but fail to replace the defective check valve, the new pump will be destined for early failure. First, begin with a cool engine to prevent burns. Turn off all accessories, including the ignition key. If your vehicle is equipped with an electric fan, make sure to disconnect the wire leading to it or remove its fuse from the fuse block. This will prevent the fan from starting up suddenly while working, which could cause personal injury. Remove any hoses and the combination valve if so equipped from the old pump. Many replacement pumps do not come equipped with a pulley, so the pulley from the old pump must be transferred to the new one. With the drive belt still on the old pump, loosen the pulley mounting bolts or retaining nut. The belt will help prevent the pulley from slipping while loosening them. Next, loosen the adjustment bracket and the pump mounting bolts. On V-belt systems, this will allow movement of the pump for belt removal. Continue removing all mounting bolts and remove the pump from the engine. With the pump out, finish removing the pulley mounting bolts or retaining nut. Remove the pulley from the pump shaft. If the pulley is pressed on, wiggling it or lightly prying on it from the back side with 2 screwdrivers should release it from the shaft. Position the pulley onto the new pump shaft. Draw the pulley onto the shaft with the mounting bolts or retaining nut. Snug up the pulley mounting bolts or retaining nut. Do not insert anything into the filter fan to hold it in place during tightening. This will result in damage to the pump and filter fan. Perform final tightening of the bolts or nut once installed on the engine. If the new pump does not come equipped with an outlet tube, reuse the outlet tube from the old pump. The outlet tube is pressed in and secured with glue. To remove it, twist the tube to break the glue seal and tap it out using a rubber mallet. Insert the outlet tube into the new pump. If the tube does not fit tightly, secure it with a small amount of thread locking adhesive. Position the new pump onto the mounting brackets. Install the mounting bolts finger tight only. Inspect the pump drive belt for wear, cracks, or deterioration. Whether severe deterioration is noticed or not, now is a good time to replace the belt. Position the drive belt onto the pump pulley and pull on the pump to apply tension to the belt. Never pry in the housing as damage to the pump may occur. With tension on the belt, tighten the mounting bolts. Most mounting bolts require about 20 foot-pounds of torque for correct tightness. Recheck the belt tension to ensure correct operation. With belt tension on the pulley, finish tightening the pulley mounting bolts or retaining nut to the correct specification. Reconnect any hoses or reinstall the combination valve if removed earlier. Inspect the finished job for proper belt alignment, tension, and pump installation. Reconnect the electric fan connector or reinstall the fuse if removed earlier. Start the engine and check the A.I.R system for proper operation. There might be a slight squeaking noise from the new pump when it is initially run. This is normal. Allow at least 500 miles for the new pump to break in and rid itself of the noise. Do not lubricate or attempt to open the replacement pump to rid the pump of this noise, as premature pump failure will result.
To replace your A.I.R pump, begin with a cool engine to prevent burns. Turn off all accessories including the ignition key and disconnect the electric fan connection. This will prevent the fan from coming on unexpectedly during the replacement. Disconnect any hoses and remove the combination valve if so equipped. Loosen the pulley bolts on the pump with the fan belt in place. Loosen the adjustment bracket and pivot bolt and remove the drive belt. Finish extracting the mounting bolts and remove the pump from the engine. Most new pumps do not come with a new pulley, so transfer the old pulley to the new pump. Snug the bolts up for now. Transfer the outlet tube and any other brackets that still may remain on the old pump. Install the new pump on the engine and loosely install the mounting bolts. Now is a good time to install a new belt to be sure of proper performance from the new pump. Tighten the new belt appropriately. With the belt tension on the pulley, tighten the pulley bolts. Reconnect any hoses or reinstall the combination valve. Reconnect the electric fan and test drive the vehicle for proper operation.
An air injection reactor, or A.I.R. pump check valve and injection tube, are the connecting links of a very important part of your vehicle's emission control system. They play a key role in reducing the pollutants that are emitted from the tailpipe of your vehicle and must be kept in proper working condition for peak engine performance and to help protect and save our environment. The A.I.R. system provides several different functions related to vehicle emissions. It reduces hydrocarbons, HC, reduces carbon monoxide levels, CO, and helps to lower nitrogen oxides, or NOx emissions. It is also used to rapidly heat up the catalytic converter on engine startup so conversion of exhaust gases can occur sooner. An air pump check valve is a one-way airflow control valve located in the air supply tubes going to the exhaust system. Its duty is to prevent exhaust gases from backing up into the diverter valve and air pump in the event of an exhaust backfire or air pump drive belt failure. If the check valve fails, the diverter valve, air tube, and air pump will be suspect for damage also. One sign of an inoperative A.I.R. system is if you fail to pass a vehicle emissions inspection. Since the A.I.R. system helps lower exhaust emissions, a check valve or manifold failure will produce higher than normal levels of hydrocarbons and carbon monoxide gases. Sometimes, a defective check valve will sound like an underhood exhaust leak. Because the check valve is allowing the passage of exhaust gases through the system, the moisture and corrosiveness of these gases will eat through the check valve and air manifold, resulting in an exhaust leak. Another sign of a defective check valve is an air pump failure. If the check valve is stuck open, exhaust gases will be allowed to enter the air pump, and the result is a locked-up pump. Quite often, an air injection reactor tube or manifold will be directly attached to the check valve. This tube or manifold is the delivery path for air from the A.I.R. pump to the exhaust system. A defective injection tube can also be recognized by an underhood exhaust leak noise. This problem may be caused by a check valve that is stuck closed, a failing diverter valve, or an air pump that is not supplying cool air to the tube. Both the check valve and the air pump should be tested whenever a leaking injection tube is found. Let's first look at inspecting and replacing the check valve. With a cool engine, visually inspect the check valve for damage due to rust and corrosion. Next, start the engine and listen for an exhaust leak coming from the check valve. If a leak is heard or damage is found, replace it. If no external damage or leaks are present, disconnect the pump outlet hose from the inlet side of the check valve. Connect a clean piece of heater hose to the inlet side of the check valve and blow through it. Air should pass freely through the valve. If not, the check valve is plugged and should be replaced. The next step for testing is to see if air will pass through it from the other direction, so removal of the valve will be necessary. To loosen rust and corrosion where the valve attaches to the injection tube, apply a liberal amount of penetrating oil onto the connection. For best results, allow at least 1 hour for the penetrating oil to soak in. Using 2 wrenches, one as a backup, loosen and remove the check valve from the air injection tube. Use caution so you do not bend or twist the injection tube. With the valve removed, blow air through it from the injection tube side. You may need a short piece of pipe in order to connect a piece of hose to it. Because it is a one-way valve, no air should pass through it from this direction. If air does pass through, the valve is defective and should be replaced. If that is the case, we recommend you also check the air pump for proper operation. Before reinstalling the valve or installing a new valve, coat any threads with anti-seize compound. Thread it onto the air tube by hand to prevent cross-threading, and tighten it using the 2-wrench method. It is important to support the injection tube to prevent damage during tightening. Lastly, reconnect the output hose to the check valve and tighten any clamps appropriately. Start the engine and check for exhaust leaks. We'll next look at inspecting and replacing the air injection tube. Most air injection tubes fail due to rust and corrosion, eventually creating an exhaust leak. With the engine running and the hood open, listen for an exhaust leak coming from the injection tube. If one is heard, inspect it for rusty areas that may be creating the leak. If found, replace the entire tube assembly. Remember, when touching any component under the hood, make sure to allow time for the engine to cool down. The air tube is attached to the exhaust manifold and therefore will be very hot if the engine has been run recently. In most cases, the fittings on the air tube will be very corroded and difficult to break loose. Before starting, apply a liberal amount of penetrating oil to the fittings. For best results, allow at least 1 hour for the penetrating oil to work in. To prevent skin knuckles and rounding off the hex nuts, use flare nut wrenches to loosen all fittings on the exhaust manifolds. Remove or disconnect the hose or fitting from the check valve. And remove the entire assembly from the engine. Match the old tube to the new one to be sure of proper replacement. Apply anti-seize compound to the threads of any fittings on the new tube. Install the new tube onto the engine, tightening all connections finger tight only. Once all connections have been started and are finger tight, finish tightening them with a flare nut wrench. Apply anti-seize compound to the threads of the check valve and reinstall the check valve on the manifold. Make sure to use the 2-wrench method when tightening. Reattach the air supply hose. Start the engine and listen for exhaust leaks. Whenever replacing the injection tube, we suggest installing a new air pump check valve. Remember, removal of the A.I.R system or failure to repair and maintain it will not only create an embarrassing situation at the emissions inspection station, you're also not doing any favors for the preservation of our environment.
Now let's quickly recap A.I.R manifold and check valve servicing. The most common sign of an A.I.R pump manifold or check valve failure is an exhaust leak coming from under the hood. The first step is to perform a visual inspection. Look for signs of rust and corrosion damage to the injection tubes and check valve. If damage is noticed, replace the necessary parts. To test a check valve, remove the air supply hose from it and using a clean piece of heater hose, try to blow through it. Air should flow freely in this direction. Remove it from the vehicle and attempt blowing through the opposite end of the valve. Air should not be able to pass through it from this direction. If it does, the valve is defective and should be replaced. When replacing an A.I.R pump check valve, coat the threads of the new one with anti-seize compound. Install the valve and tighten it securely. Reconnect the hose and you're done. Now let's review A.I.R manifold replacement. Once again, begin with a cool engine. Spray a rust penetrating oil on the threads of the fittings. Allow the penetrant to soak in for at least 1 hour. With the correct size flare nut wrench, loosen and disconnect the tube fittings. Disconnect the hose or fitting from the check valve and remove the manifold from the engine. Compare the new and old manifolds to be sure of proper fit. Apply anti-seize compound to the threads of the fittings on the new manifold. Start all of the fittings in the threads by hand. Once all of them have been started, tighten them securely using a flare nut wrench. Coat the threads of the check valve with anti-seize compound and reinstall it onto the manifold. Tighten it using the 2-wrench method. Reattach the A.I.R injection hose to the check valve. Start the engine and listen for leaks.
A common engine performance control used on today's vehicles is a ported vacuum switch, PVS, or thermal vacuum switch, often referred to as TVS. Ported vacuum or thermal vacuum switches are located in the vehicle's cooling system and can commonly be found in the radiator, the intake manifold, or on the thermostat housing. Their duty is to supply or block vacuum to a certain component as the engine coolant reaches a preset temperature. Thermal vacuum switches have been used on vehicles since the early 60s to control items like distributor vacuum advances, the E.G.R system, heated air intake systems, and canister purge operation, just to name a few. Symptoms of a failing thermal vacuum switch can include poor performance or economy, surging while highway driving, engine knock or detonation, rough idle, and a stumble or hesitation on acceleration. The first step for testing a thermal vacuum switch is to perform a visual inspection. Look for cracked or broken vacuum ports, which often happen because the plastic upper body portion of the switch has become brittle. This is caused by the continuous hot and cold cycling experienced during normal engine operation. Testing a thermal vacuum switch can be performed on or off the vehicle. To test the switch on the vehicle, you will need a hand vacuum pump and a vacuum gauge. With the engine cold, remove the vacuum supply line from the switch, plug it, and in its place, connect the hose from the hand vacuum pump. Remove one of the other vacuum lines on the switch, and in its place, connect a vacuum gauge. Apply 20 inches of vacuum. If the switch is normally closed when it is cold, start the engine. As the engine warms up, the switch should purge vacuum from the hand vacuum pump and transfer it to the vacuum gauge. If the switch doesn't originally hold vacuum, it may be defective or it is normally open when it is cold. If it's normally open cold, then it should not allow the passage of vacuum after the engine is fully warm. In either case, you should be able to notice a change in operation from when the switch is cold to when it is hot. If it never holds vacuum, doesn't transfer vacuum as the engine warms up, or both gauges remain at the same reading all the time, replace the switch. Testing it off from the vehicle can be performed in the same manner by using a cigarette lighter to warm the capsule on the sensor. Once again, the switch should either transfer or block the vacuum from the hand pump as the tip of the switch is heated up. Replacing a thermal vacuum switch only requires a few simple hand tools. They include the correct size wrench for removal of the old switch, a drain pan, some Teflon thread sealing tape, and the correct replacement switch for your vehicle. First, begin all repairs with a cool engine. Then place a pan under the radiator and drain a sufficient amount of coolant from the radiator to prevent spillage when removing the switch from the cooling system. Remove any brackets or fan shrouds as needed to access the switch. Then, disconnect the vacuum hose connection or connections from the switch. You may wish to label the hose locations to be sure of correct positioning on the new switch. With the correct size wrench or socket, loosen and remove the switch. Excessive scale and corrosion buildup on the bottom of the sensor can act as an insulator, causing the switch to send a late or no signal. To help prevent scaling and deposits on sensors or switches, we suggest a complete flush and refill of the cooling system every 2 years. Compare the old and new switches to ensure proper replacement. Place a small dab of pipe sealant or Teflon thread sealing tape on the threads of the new switch. To prevent cross-threading, begin by installing the new switch by hand. Do not, however, apply pressure on the vacuum ports of the switch, as permanent damage may occur. Carefully tighten the new switch with the proper size wrench. Reconnect any vacuum hose connections. Reinstall any brackets or the fan shroud if removed. Refill the cooling system with the antifreeze removed earlier, and you're done.
Let's briefly recap the steps involved for testing and replacing a ported thermal vacuum switch. First, perform a visual inspection. Look for cracked or broken vacuum ports. To test the switch on the vehicle, connect a hand vacuum pump to the vacuum source port on the switch and connect a vacuum gauge to one of the other ports on the switch. Apply 20 inches of vacuum to the switch. Now start the engine. If it is a normally closed cold switch, the switch should transfer vacuum from the hand pump to the vacuum gauge when the engine warms up. If it is a normally open cold switch, it should stop the flow of vacuum once the engine is warm. In either case, there should be a change in the operation of the switch from when it is cold to when it is hot. If it never changes, replace the switch. Whenever working under the hood, always begin repairs with a cool engine. Drain the coolant from the radiator into a clean drain pan. Disconnect the vacuum hose connections from the switch. Label their locations to ensure proper reconnection. With the correct size wrench, remove the switch. Compare the new and old switches to be sure of proper replacement. Place a small dab of pipe sealant on the threads and reinsert the new switch by starting it in the threads by hand. Carefully tighten the new switch. Reconnect any vacuum hoses removed earlier. Lastly, refill the cooling system with the antifreeze earlier removed.
The exhaust gas recirculation, or E.G.R. valve, is one of the engine's most important emission controls for reducing oxides of nitrogen, or NOx emissions. The E.G.R. system recirculates a portion of the exhaust gases into the intake manifold, reducing the combustion temperature and therefore decreases NOx emissions. Common engine drivability symptoms associated with a defective E.G.R. valve include an engine that idles rough or stalls at stop signs, poor engine performance or surging at highway speeds, and uncontrollable pinging or detonation. An E.G.R. valve should be inspected every 12 to 15,000 miles for proper operation. There are three basic types of E.G.R. valves being used on today's vehicles: a ported vacuum type, positive back pressure, and negative back pressure. As a result, there are different testing procedures for each depending on the type. This video will demonstrate how to test the two most common, the ported and the negative back pressure types. To determine what type of E.G.R. valve your vehicle is equipped with, refer to a Haynes manual. Let's look at how to test E.G.R. valves on the vehicle. The tools you will need include a hand vacuum pump, an inspection mirror, and a service manual for your particular vehicle. Whenever working on a vehicle with the engine running, make sure you are working in a well-ventilated area. Place the vehicle in park or neutral and set the parking brake. First, inspect all vacuum hoses going to the E.G.R. valve for cracks, kinks, broken sections, and proper connection. If damage is found, repair or replace the hose. First, we'll look at testing a ported E.G.R. valve. Run the engine until it is at operating temperature and shut it off. Disconnect the vacuum hose from the valve. You may want to wear gloves to prevent burns. In its place, connect a hand vacuum pump. Apply 10 inches of vacuum to the valve. The diaphragm plate should move upward, opening the valve, and should remain open for at least 20 seconds. If the diaphragm plate cannot be easily observed, use an inspection mirror to ease viewing. If the vacuum reading drops within 20 seconds, or the diaphragm plate does not move up, there is a leak in the diaphragm. Replace the E.G.R. valve if a leak is found. Release the vacuum from the pump. Start the engine, and again apply 10 inches of vacuum to the valve. As the valve opens, the engine RPM should drop, causing the engine to stumble or stall. This indicates the valve is operating properly. If no change is noticed, the valve is not working properly and must be replaced. Next, we'll demonstrate how to test a negative back pressure E.G.R. valve. With the engine off, disconnect the E.G.R. valve vacuum hose, and in its place, connect a hand vacuum pump. Apply 10 inches of vacuum to the valve. The diaphragm plate should move upwards, opening the valve, and should remain open for at least 20 seconds. If the diaphragm plate cannot easily be observed, an inspection mirror will ease viewing. If the vacuum reading drops within 20 seconds, or the diaphragm plate does not move, there is a leak in the diaphragm. Replace the valve if a leak is found. With the help of an assistant, again, apply 10 inches of vacuum to the valve, and immediately start the vehicle and observe the diaphragm plate. The plate should move downward, closing the valve during engine cranking and startup. If the diaphragm plate does not move downward, replace the valve. Many late model vehicles are now coming equipped with either an electronic or digital E.G.R valve. These types of E.G.R valves are controlled by the vehicle's onboard computer and therefore require different testing procedures. Refer to a service manual for specific testing procedures on these types of E.G.R valves. An E.G.R valve may also be tested off the vehicle using a Tomco E.G.R tester. Refer to the directions included with the E.G.R valve tester for detailed procedures. The directions cover the 3 common types of E.G.R valves and list the specific tools needed to bench test each of them. If you remove an E.G.R valve for testing and find it is okay, always reinstall the E.G.R valve using a new gasket. This will prevent exhaust leaks around the base of the valve.
Now let's briefly review the steps for testing a ported E.G.R valve. First, inspect all vacuum lines and replace any that are cracked or broken. Because certain checks will be made with the engine running, make sure the automatic transmission is in park, or if it's a standard transmission, in neutral with the parking brakes set. Also, always stand to the side of the vehicle when the engine is running and work in a well-ventilated area or outside. Run the engine to reach operating temperature, then shut it off. Disconnect the vacuum hose leading to the valve and in its place connect a hand vacuum pump. Apply 10 inches of vacuum to the valve and watch the diaphragm plate. The plate should move upward and the vacuum applied should remain constant for at least 20 seconds. If no diaphragm movement is noticed or it will not hold vacuum, replace the valve. Then start the engine and allow it to idle. Once again, apply 10 inches of vacuum to the valve. As the valve opens, a significant drop in engine RPM should be noticed. If there's no change in RPM, replace the valve. To test a negative back pressure E.G.R valve, once again, connect a hand vacuum pump to the valve and apply 10 inches of vacuum. If the vacuum plate does not move or a drop in your reading is observed within 20 seconds, replace the valve. Then start the engine and again observe the diaphragm plate. The plate should move downward, closing the valve. No movement means the valve is defective and should be replaced.
E.G.R, or exhaust gas recirculation valves, are commonly located on or near the intake manifold and have a single vacuum hose and round vacuum chamber. As a preventive maintenance measure, we suggest replacing your E.G.R valve every 30 months or 30,000 miles, whichever comes first. Whenever working under the hood, we suggest starting repairs with a cool engine to prevent burns. Then locate the valve itself. Remove and inspect the vacuum hose attached to the top of the valve. Replace the hose if it's brittle or cracked. Remove the mounting bolts that attach the valve to the intake manifold and remove the valve from the engine. With the valve removed, remove the old gasket and clean any material left on the mounting area. Due to advanced technology and design changes, your new E.G.R valve may appear slightly different than the old one. Please make sure you read and follow the instructions included with your new E.G.R valve for details about the installation on your particular vehicle. When installing your replacement E.G.R valve, record the identification number from your old valve on the label provided. Place the label on the new valve as shown and apply the protective cover over the label. Then, set the new gasket in place and position the new valve on the manifold. Apply a light coat of anti-seize compound to the threads of the bolts and reinstall them in the threads by hand. Securely tighten the mounting bolts with the appropriate wrench or socket. Reconnect the vacuum hose and test drive the vehicle to be sure of correct operation.
As a preventative maintenance measure, we recommend replacing your E.G.R valve every 30,000 miles. To prevent burns, begin your replacement with a cool engine. Locate the valve, remove and inspect the vacuum hose leading to it. If it's brittle or cracked, replace it. Remove the mounting bolts and the valve can be removed from the engine. Clean any old gasket material from the valve mounting surface. Due to advanced design changes, your new valve may appear slightly different than the old one. Refer to the instructions included with your new valve for details about the installation on your vehicle. Record the identification number from your old valve on the label provided and place the label and its protective cover on the new valve. Apply a light coat of anti-seize compound to the bolts. Position the new gasket and valve on the engine and begin threading the bolts in by hand to prevent cross-threading. Securely tighten the bolts. Reconnect the vacuum hose and test drive the vehicle.
Our drivability problem this time is on a Chrysler vehicle, Jim. And what we've got is we've got the kind of that rotten egg smell or odor coming out of the tailpipe, the poor fuel economy, and the driver just complained about the throttle response just isn't what it used to be. Now I use the key method to pull the codes on the car, on, off, on, off, on. I came up with a code 22. And when I looked in our book, a code 22 said O2 system full rich or full lean. So boy, we know where to start, don't we?
We sure do. It's in the oxygen sensor circuit, but we don't really know where. Could be a wire, a computer problem, could even be the oxygen sensor itself. So best thing to do is remove it from the vehicle and take a look at it and see what color it is. Maybe that'll help us determine the problem.
Sure, there's three things that you can do to an oxygen sensor. First thing is you can perform a visual inspection.
Right. Second
thing is you can do an on-the-bench test. And the third thing is you can test it on the vehicle, and we'll do all three of those right now.
Well, let's take a look at the colors first. Here's one we took from a vehicle that has sort of a grayish color. You can see a little bit of a coating on it, but that's normal, Scott. That shows just it's been in there for a long time doing its job, and it has normal combustion type color.
Okay.
Now here's another one that is normal also. It doesn't have quite the amount of deposits on. It's got a slightly reddish tint to it, and that reddish color comes from the gasoline additives that we have nowadays. So that's a pretty good looking oxygen sensor too. It's just been in there a long time doing its job, and we had to replace it just as normal maintenance.
Okay.
But here's one that's all black. See that rich black color? And that comes from an over-rich mixture. And it has coated the whole thing with carbon.
Yep.
So maybe this is part of the problem that we're having on the vehicle that you just described.
Okay, now we've got some lighter colored ones over here too.
Yeah, now this one here is just a slight hint of gray, and it looks like someone's been running leaded gas in this car.
Okay, and that'll contaminate the sensor, and that could create our problem that we're having right now. The sensor is not as active as it used to be because it is now contaminated by leaded fuel.
Right. And the last one here that we can look at is one that's kind of a chalky white color. And this usually shows contamination from using antifreeze that's leaking through the head gasket someplace, or anywhere where it gets into the cylinders.
Sure.
Sometimes using a silicone-based sealing compound that is not the right type will also cause this type of contamination. So silicone or antifreeze will turn them white.
Okay. Now how about our bench test? We finished our inspection and determined that, let's check this one right here. This one came out of the vehicle and you said it looked fairly well.
Yeah, it really did. Now, doing it on the bench simply requires the use of a propane torch and also a voltmeter, a digital voltometer.
Okay.
Now, the whole idea here will be to put the tip of the oxygen sensor into the flame where there is no oxygen. Now, on the car, an oxygen sensor that's detecting a lean mixture will produce a low voltage, and one that's detecting a rich mixture will produce a high voltage. Now, there's no oxygen in the flame, so that's kind of like a rich mixture.
Okay.
So as we stick it in the flame, the voltage should come up. And as I pull it out of the flame, the voltage should go down, and that's our test. But there's a time limit on this. When I put it in the flame, the oxygen sensor must be able to produce 9/10 of a volt within 1 minute. And when I pull it out of the flame, the voltage must drop within 3 seconds to where it was before. It's a very, very simple test, and we can do that together right now.
All right, and the other thing we're doing is we're actually heating the oxygen sensor tip to 600 degrees Fahrenheit, which has to be done for a bench test or an on-the-car test, either way. Before we light the torch, I'm just going to put my safety glasses on, and we'll get this lit, and I'll point this away from us. Okay, we have that lit now.
I'm turning the voltmeter on to the lowest voltage scale, the 2-volt scale, because these oxygen sensors only produce about 1 volt or so.
Sure.
So you need to be on your low scale. Then we're going to connect the red lead of the voltmeter to the wire end, in this case, or the terminal that you would have. And you must remember to use the black wire. Sometimes an oxygen sensor has more than 1 wire. Some have little heaters in. So always remember to use the solid black wire.
Good point.
And then connect your ground lead of the voltmeter to the shell of the oxygen sensor. You can just hold it like this.
Okay.
Now I'll insert it in the flame and we'll see if this oxygen sensor can produce 9/10 of a volt within 1 minute.
Okay. Well, it's already starting to produce a voltage. 5, 6, 7, 8, 9/10 of a volt already.
Okay, so far
1
so
volt.
good.
Yep.
So I'm going to pull it out of the flame and we'll see if it drops.
1001, 1002, 1003. And it's right back down to 0.008 and dropping.
Okay, great. So I think that this one here, although it still functions, has just been in there quite a long time and was replaced just because of maintenance. So this is a good oxygen sensor, and that's how you can tell if they're good or bad right on the bench.
Okay.
Now one thing I'll do though is put this down into an ashtray or someplace where it can cool off, because they're quite hot for a while.
All right. Now there's an on-the-vehicle test that can be performed also. Why don't we head out in the garage and show them that one?
Okay.
Now, along with a simple bench test, you can also test your O2 sensor right on the vehicle, and we're going to demonstrate that right now, right, Jim?
That's right. Now, basically what we're going to need, Scott, is a voltmeter set on the 2-volt scale because the O2 sensor produces a very small voltage. And I'm going to connect the voltmeter first to a good ground. The negative lead gets connected to a good engine ground.
Sure.
And then I'm going to reach over and unplug the O2 sensor lead and connect the positive lead of the voltmeter to the O2 sensor's lead. Now we'll be able to measure the voltage while it's right in the engine. Now we're going to have to run the vehicle and change the air-fuel mixture ratio. A simple way to do that would just be to create a vacuum leak.
Sure.
And there's a vacuum port right here on the top of this engine with a little rubber cap on. So if you have one of these on your car, there's a little clip that you can use a pair of pliers to remove and get that out of the way, and then simply pull the little boot off. And that will create the vacuum leak that you need to change the mixture. So I'll start the car and we'll do that.
All right. Now, we've previously run this engine for a little bit of time to warm it up, too. Okay. You might need to run the engine for a little additional time, and our meter's starting to come up now. So I think our O2 sensor is warm enough. And it does have to be at least 600 degrees Fahrenheit for this test to work.
Now I'm going to go ahead and open up the vacuum port, and we should watch the numbers drop as we lean the mixture.
Yep, going way down. Put your finger over it, plug the vacuum leak, numbers go back up. Way down, and back up.
Now, as you can see, the engine almost stalled on this test, and on some vehicles it actually would stall. So on those vehicles, we'll have to do something called a propane enrichment test.
Sure.
And so I'm going to take this valve, which we have screwed to a propane bottle. It's a regular propane bottle with a special valve on it for doing this test, and connect it to the vacuum port.
Okay, now we have a slight vacuum leak introduced, so we're seeing a real low voltage on the voltmeter, which is a signal of a lean mixture. Now, if we open the propane bottle up, our reading should go up. There it goes, way up.
And as I shut it off, it goes back down.
Way back down.
But this gives us the opportunity then to test an O2 sensor on the vehicle with either a vacuum leak or a propane enrichment test.
Let's review the test procedure for an oxygen sensor that has been removed from the vehicle. The first step is to visually inspect the oxygen sensor. Normal coloration will be light tan. White, black, red, or light gray deposits are sign of a contaminated sensor. Connect the red lead of the digital voltmeter to the black lead from the sensor. Connect the black lead from the digital voltmeter to the body of the sensor. Set the meter to the 2-volt scale. Heat the sensor tip in the flame of a propane torch. The voltage should exceed 0.9 volts within 1 minute. Remove the sensor tip from the flame. The reading on the voltmeter should reach 0.1 volt or less within 3 seconds. If not, replace the sensor. Now let's review the testing procedure for an oxygen sensor that is still installed in the vehicle. Connect the red lead of the voltmeter to a pin that is back probed into the oxygen sensor connector. Connect the black lead to a good engine ground. Locate a good manifold vacuum source. Start the engine and run it until the meter reading begins to toggle over and under 0.5 volts. Create a vacuum leak at the port or source located earlier. Observe the meter reading. The voltage should drop below 0.1 volt briefly with the vacuum leak and should rise above 0.5 volts when the vacuum leak is plugged.
Your vehicle's oxygen sensor is located in the exhaust manifold or pipe ahead of the catalytic converter. An oxygen sensor resembles a spark plug and has 1, 2, or 3 wires attached to it. For peak engine performance, we recommend replacing your oxygen sensor every 25 to 30,000 miles or every 2 years. The items you will need to replace your oxygen sensor include a socket set and torque wrench, an oxygen sensor socket, some penetrating oil, a wire cutter and crimper, some anti-seize compound, a cigarette lighter, a soldering gun and solder, and the correct replacement oxygen sensor for your vehicle. The first step in replacing your oxygen sensor is to start with a cool engine. In most instances, the oxygen sensor will be readily accessible. However, we remove the air cleaner for better viewing of the procedure. Then locate the sensor and spray some penetrating oil on the fitting to help loosen corrosion. Oxygen sensors are available with original equipment leads or as a universal type. Our demonstration will detail the steps involved for the installation on a universal type. Cut the existing wire or wires as near the sensor as possible. Disconnect the sensor connection on the other end of the wire and place the wire on the workbench. With a socket of the correct size, remove the old sensor from the exhaust manifold. For ease of removal, you may want to use a special oxygen sensor removal socket as shown. Some replacement sensors may come with fewer leads than the one you removed. For installation of these type, please refer to the instructions included with it. Slide a piece of heat shrink tubing over the new oxygen sensor wire and strip about 1/4 inch of insulation from the ends of the wires that are to be connected together. Reconnect the old wire to the new sensor with a crimper and butt-type wire connector supplied. We suggest soldering this connection with rosin core solder for a positive corrosion-free connection. For wiring details on your particular vehicle, consult the complete wiring instructions included with your new oxygen sensor. Then slide the heat shrink tubing over the connection and collapse the tubing with a heat gun or lighter until it shrinks and weather seals the connection. Most oxygen sensors come with anti-seize compound on the threads, but if yours doesn't, place a small dab of non-volatile anti-seize compound on the threads prior to installation. Do not, however, allow the anti-seize compound to get on the bulb of the sensor. Install the new sensor in the threads, starting it by hand, and tighten it with a torque wrench to 30 foot-pounds. Reconnect the sensor wire at the factory connector, and make sure the wire is routed away from any moving parts and the exhaust manifold. Reinstall the air cleaner assembly if earlier removed, and start the engine to ensure proper installation of the sensor. For a written version of testing and replacing your oxygen sensor, pick up your free copy of Champion Auto Store's Tech Tip number 37.
Now let's review the steps involved in replacing an oxygen sensor. As always, begin with a cool engine. Cut the old wire from the oxygen sensor near the sensor itself. Disconnect and remove the old sensor wire at the snap lock connector. Remove the old sensor from the exhaust manifold or pipe. Strip a 1/4 inch of insulation from the electrical wire attached to the sensor and also the wire you removed from the vehicle. Reconnect the electrical wire by soldering and use a heat shrink insulator. Apply a non-volatile anti-seize compound to the threads of the new sensor. Install the new sensor using an oxygen sensor socket and torque to the correct specification. Reconnect the wire and test drive the vehicle to ensure proper replacement.
Okay, now if you've got a vehicle that's running too rich, you might have some black smoke out of the tailpipe, and on this vehicle it's getting pretty poor mileage, Jim. When I went in and pulled the trouble codes out of the computer, I got a code 15. When I went to my trouble code chart, it simply says right here, code 15, open coolant sensor circuit. Now you've got a quick test of that coolant temp sensor, don't you?
Sure do. It's another one of the 2-minute tests that you can perform at home to find out if your coolant temperature sensor is working.
Okay.
Now here's one, just like the one that's in this vehicle here. And of course it's out of the vehicle, it's not warm, it's cool. Inside of a coolant temperature sensor is a thermistor, which is a device that changes its resistance with temperature.
Sure.
Now in this particular case, as I said, it's cool, so it's going to have a specific reading on the ohm meter. I'll take our meter and put it to about the 20,000 ohm scale, or the 20K scale,
okay,
and connect one lead to the body and the other one to the terminal, and we'll get a specific reading. In this case, about 1,930 or so ohms.
Sure.
Now remember, this is a cool one. This engine is quite warm. It's been running. So to illustrate the difference between a cool one and a warm one, we simply take and connect the black lead to a good ground, the positive lead to the sensor terminal, and here we can see we're at about 460 or 470 ohms. Quite a difference.
Yeah, it certainly is. Now, when you actually perform this test on your vehicle, you're going to be running the engine. You connect your meter up, you're going to run the engine for 2 minutes, and you're going to look for a 200 ohm difference within that 2-minute period. For sake of illustration, we did it this way. Now, if you don't find any change, boom, that's your problem. Replace the coolant temp sensor, and you're on the road again. If you do find a change, your coolant temp sensor is okay, and then you've got to get back in the book and do a little bit of work and go to your actual trouble code chart and follow your diagnostic chart out to find the problem. In this case, you'd probably find an open coolant sensor circuit wire or something in the ECM.
To test a coolant temperature sensor on the vehicle, disconnect the wire from the sensor and attach the red lead from a digital volt-ohm meter to the sensor terminal. Attach the black lead to a good engine ground near the sensor. Set the meter to the 20K scale. Observe and record the reading with the engine at ambient temperature. Start and run the engine for 2 minutes. Observe and compare the new reading to the first one taken. The minimum difference for a good sensor is 200 ohms. If the difference is less than 200 ohms, replace the sensor.
To replace your engine coolant temperature sensor, the tools you will need include a standard or metric wrench set, a hex wrench set, a regular blade screwdriver, liquid pipe thread sealant, a gallon of antifreeze, a large drain pan, and the correct coolant temperature sensor for your vehicle. Whenever working on your vehicle, always start repairs after the engine has cooled down. This will prevent personal injury due to hot engine coolant. The first step whenever working on the electrical system is to turn off all the accessories, including the ignition key. Then, disconnect the negative battery cable. This will keep spike voltages from damaging other components and will prevent the electric cooling fan from engaging during repairs. Before disconnecting the negative battery cable, be sure to write down any pre-programmed electronic radio stations on a piece of paper. This will allow quicker reprogramming when repairs are completed. On most vehicles, the engine coolant temperature sensor will be located either in the coolant passages of the intake manifold or near the thermostat housing. Next, open the radiator drain and lower the level of the fluid in the system. This will prevent coolant from spilling out onto the engine after the sensor has been removed. Make sure you have a drain pan to catch the old coolant. Then remove the radiator cap. On many late model vehicles, a bleeder plug must also be removed from the thermostat housing. Release the locking tab on the electrical connector and remove the electrical connector from the engine coolant temp sensor. Using a wrench or the appropriate socket, remove the old sensor. Compare the old sensor to the new one to be sure of correct replacement. Inspect the old coolant temperature sensor tip for scaling and deposits. If scaling is evident, we strongly recommend the cooling system be flushed and the engine coolant also be replaced to prevent scaling and deposits from forming on the new sensor. If the new temperature coolant sensor's threads are coated with a pipe sealant to prevent coolant leakage, no additional sealer is necessary. Install the new sensor and tighten it securely. Before reconnecting the electrical connector, inspect the connector for signs of damage and for wetness. If the connector is wet from engine coolant, inspect the entire wire for corrosion and replace as necessary. Reconnect the electrical connector to the new sensor, making sure the locking tab is secure. Add a new coolant mixture of 50% water, 50% antifreeze to the radiator until it reaches the radiator cap seat. We recommend you do not reuse the old engine coolant that was removed. On vehicles where a threaded bleeder plug was removed, add coolant into the radiator until it reaches the bottom of the bleeder plug hole. With sealer on the threads, reinstall the bleeder plug in the hole and tighten it securely. After installing the bleeder plug, continue to fill the radiator until it reaches the radiator cap seat. Reinstall the radiator cap. On vehicles with a coolant reservoir, fill with new engine coolant until the level is between the minimum and maximum marks. Reconnect the negative battery cable. Start the engine and run until normal operating temperature is reached. With the engine idling, add coolant to the reservoir as needed. And lastly, reprogram the electronic radio stations if so equipped.
To replace your coolant temperature sensor, follow these steps. Turn off all accessories and make sure the ignition key is in the off position. Locate the coolant temperature sensor, which can be found in the engine block. Drain the engine coolant from the radiator. Disconnect the coolant temperature sensor electrical lead. Remove the sensor from the engine. Once removed, inspect the tip of the sensor for scaling or rust deposits. If any are found, flush and refill the cooling system. Compare the new and old sensor to ensure a proper fit. Coat the threads of the new sensor with a liquid pipe sealer and install it in the engine block, being sure to start it in the threads by hand. Tighten the sensor securely. Reconnect the electrical connection at the sensor. Refill the cooling system with a new mixture of antifreeze and water.
The idle air control motor, or IAC motor as we'll call it, is a computer-operated valve that controls bypass air around the throttle plate to increase or decrease the idle speed for different conditions. Symptoms of an idle air control problem include erratic or noticeably high or low idle speeds. The items you will need to test and service an IAC motor include a small flat blade screwdriver, a digital voltometer, a standard or metric wrench set, some spray carburetor cleaner, and a clean shop towel. Make sure the vehicle is in park or neutral and the parking brake is set. The first step in testing your IAC motor is to check the basic operation with the engine cold. Start the engine and verify that the engine runs at high idle. This may only last a few seconds or may last up to 45 seconds. Allow the engine to continue running. The idle speed should automatically drop to its low RPM setting when the vehicle warms up. This is one sign the IAC motor is working. With the vehicle warmed up, turn the air conditioning on maximum. On vehicles without air conditioning, turn the steering wheel all the way hard left or hard right. In either case, the idle speed should increase to compensate for the extra load on the engine. Once again, this increase is caused by a properly functioning IAC motor. Now, turn the air conditioning off or straighten the wheels. Allow the engine to continue running. Locate the IAC motor on the throttle body or port fuel injection unit. Carefully grasp the wire harness connected to the IAC motor and wiggle the wires. Listen for a change in the idle speed that will indicate a poor or partially broken connection. If any changes are noticed, replace or repair the electrical connection and retest. Shut the engine off and allow it to cool down. While you are waiting for it to cool, disconnect the negative battery cable. Use a small flat blade screwdriver to release the locking tabs and disconnect the harness from the motor. Inspect the connection for corrosion and clean as needed with electrical spray cleaner. Remove the mounting bolts, if so equipped, and remove or unthread the IAC motor from the throttle body assembly. On models that have an IAC motor with an exposed pintle, such as this General Motors, begin by examining the pintle closely. Scrapes or rub marks on only one side are an indication of a bent shaft and would require replacement of the motor. Now is also a good time to clean any deposits from the pintle and its seat inside the injector housing. Oftentimes, these deposits can create idle speed problems. Spray oxygen sensor safe carburetor cleaner onto a shop towel and wipe away deposits that may be on the pintle itself. Use the same method to clean deposits from the pintle seat area of the injector. Do not, however, spray carburetor cleaner directly into the cavity. If the deposits were heavy, once they are clean, reinstall the IAC motor and repeat the steps discussed earlier. If you are using a large wrench to tighten the IAC motor, be extremely careful not to over-tighten it, as damage to the IAC motor will result. Now, reinstall the mounting bolts earlier removed and reconnect the electrical connector. If you have an internal pintle design IAC motor as shown, cleaning is not recommended because you may cause damage to the motor. If idle problems still persist, connect an ohmmeter across the diagonally positioned terminals. Polarity is not important. Set the ohmmeter on the low scale. Your reading should be over 20 ohms if the motor is good. Repeat this same procedure across the other two terminals. If the reading is less than 20 ohms either time, replace the IAC motor. If your vehicle has a 2-pin electrical connector, attach the ohmmeter leads to the terminals. A reading of 7 to 13 ohms should be obtained on the low scale. Lastly, set the ohmmeter to the 20K or high ohm scale. Connect one lead to one of the terminals and the other lead to the IAC motor housing. A reading over 10,000 ohms should be obtained. If any of your readings are not within specifications, replace the IAC motor.
The first step for testing your idle air control motor is to start the engine when it is cold and verify that it momentarily runs at high idle. As the engine becomes warm, the idle should return to its low setting. This is a sign of a correctly performing IAC motor. With the engine running, wiggle the wires connected to the IAC motor and listen for a change in RPM. A change indicates a bad or broken connection. Next, turn on the air conditioning or turn the steering all the way hard left or right. Once again, a rise in engine RPMs indicates a properly functioning IAC motor. To service an IAC motor with an exposed pintle, remove it from the throttle body. Clean any carbon deposits from the pintle and its seat within the throttle body with a towel saturated in carburetor cleaner. Reinstall the IAC motor, being careful not to over-tighten, and retest. Should problems still persist, you can check the resistance of the motor windings with an ohmmeter. For a 2-terminal IAC motor, the reading across the terminals should fall between 7 and 13 ohms on the low scale. On a 4-pin motor, check the reading between the diagonally positioned terminals. A good motor will read over 20 ohms. Lastly, with the ohmmeter set on the 20K scale, connect one lead to a terminal and the other to the IAC motor housing. A reading over 10,000 ohms should be obtained. If any readings are not within specification, replace the motor.
To replace an idle air control motor, the tools you will need include a small, flat blade screwdriver, a standard or metric wrench set. For some GM vehicles, you'll need a small ruler and, of course, the correct replacement IAC motor for your vehicle. To prevent burns when working under the hood, always start repairs with a cool engine. Begin by labeling and removing any hose or electrical connections to the air filter housing, and remove the housing if it obstructs access to the IAC motor. Not all models require this. Next, locate the IAC motor on the injection unit. Before proceeding any farther, make sure the ignition switch is in the off position. Use a small, flat blade screwdriver to release the locking tabs and disconnect the electrical harness from the IAC motor. Remove the IAC motor from the injection unit. Compare the old motor to the new one to be sure of correct replacement. The most critical area to compare is the pintle on the external type, as 3 different designs are used. One has a single taper, one has a dual taper, and the other has a blunt style of pintle. Your replacement must be the same type or drivability problems will result. Next, measure the distance between the tip of the pintle and the end of the motor housing on the new motor. It should be extended no more than 1 1/8 of an inch. If the pintle is out too far, it must be adjusted. There are 2 methods for adjustment of the IAC motors on most vehicles. This type, with a collar at the electrical connection, is adjusted by simply pushing firmly in on the end of the pintle. This type without a collar is adjusted by holding the spring down with one hand and turning the pintle counterclockwise with the other. Before installing a new IAC motor of this design, use a clean shop towel soaked in oxygen sensor-safe carburetor cleaner to remove any deposits that may be built up in the seat area of the injector. If you have an internal design IAC motor, cleaning is not recommended. With the pintle seat clean and the IAC motor adjusted, use a new gasket and screw the new motor into place. Always begin turning components in by hand to prevent cross-threading. Tightening most IAC motors requires the use of a large wrench. Be extremely careful not to over-tighten it, as damage to the IAC will result. Reconnect the electrical harness to the IAC motor, making sure it is firmly seated. Now, reinstall the air filter housing if it was removed earlier, and reconnect all hose and electrical connections. Start the vehicle and allow it to run until it reaches operating temperature. Then test drive the vehicle at a constant speed over 45 miles per hour. This will allow the onboard computer to reestablish a reference point for controlling the IAC motor.
Let's quickly recap the steps necessary to replace your idle air control motor. Always begin with a cool engine. Make sure all accessories are turned off, including the ignition key. Locate the IAC motor and disconnect the electrical connection. With a large wrench, remove the IAC motor from the injection unit. Compare the old and new motors to be sure of correct replacement. If the motor is adjustable, measure the throw distance of the old motor. Adjust the new motor to match this distance. Clean the pintle seat with a towel soaked in carburetor cleaner and install the new IAC motor in the housing. Be careful not to over-tighten the IAC motor, as damage could result. Reconnect the electrical connector and test drive the vehicle at a steady speed over 45 miles per hour to allow the onboard computer to reestablish a reference point.
To test and replace your catalytic converter, you'll need a 3/8 inch drive socket set, a set of flat wrenches, some penetrating oil, a rubber mallet, a wire brush, a block of wood, safety glasses, a pair of gloves, a jack and a set of jack stands, a small screwdriver, a propane torch, a vacuum gauge, the correct catalytic converter, and the correct size U-bolts for your vehicle. If your vehicle has an air tube attached to the catalytic converter, you will also need an air tube repair kit. Before you test or replace your catalytic converter, start with a cool engine, preferably after the vehicle has not been driven for 12 hours, as catalytic converters get very hot during vehicle operation and they maintain heat for a long while afterwards.
First, check for excessive restriction in the exhaust system. Attach a vacuum gauge to a fitting or port that has full engine vacuum, such as directly from the intake manifold or a port tapped in below the throttle plates. Start the engine and observe the reading on the gauge. A normal reading for most vehicles at idle is about 17 to 19 inches of vacuum. Now raise the engine speed to over 2,500 RPMs and hold it steady. The difference in the at idle reading and the at 2,500 RPMs should not differ more than 3 inches of vacuum. An exhaust restriction, such as a plugged converter, will cause a significantly lower reading. Next, you'll need to raise the vehicle and put it on jack stands. This will enable you to work under the vehicle safely. Never work under a vehicle with only the jack for support. To ease viewing in our example, we have placed the vehicle on a hoist. Wear safety glasses whenever working under a vehicle. Now locate the catalytic converter. It will normally be found between the exhaust pipe and the muffler. Examine the converter for physical damage. Tap on it with a rubber mallet and listen for any loose pieces inside of it. If the insides of the converter have broken loose, it must be replaced. To determine if the converter is the cause of the exhaust restriction, drill an 1/8-inch hole in the pipe a couple of inches before the converter. With the engine running at idle, measure and record the exhaust gas pressure at the point of your drilled hole. If the exhaust system is free from restrictions, you will get a very low or no reading on the gauge. If your reading is above a half pound of pressure, continue this procedure. Now use a 1/8-inch aluminum rivet to plug the first hole. Then drill another 1/8-inch hole in the exhaust pipe after the converter. Once again, measure and record the exhaust back pressure at the second hole with the engine idling. If the difference between your first reading and the second reading exceeds 1/2 pound of pressure, the converter must be replaced. The first step in the replacement is to apply penetrating oil to the flange nuts and U-bolts and allow it to soak in. Also apply penetrating oil to the air tube nuts if so equipped. It is best to do this a night before to allow the oil to work in. Remove the flange nuts and bolts from the forward end of the catalytic converter. Remove the old flange gasket. The old gasket may stick to the flange, but can easily be pried off with a small screwdriver. Remove the U-bolt from the rear joint between the converter and the exhaust pipe. Use caution. U-bolts get very rusty and can break off suddenly. Always wear work gloves whenever handling exhaust parts. The catalytic converter will most likely be too rusted to the exhaust pipe to be tapped off with a mallet. To ease removal, heat the neck of the converter with a propane torch to expand it enough to twist the converter loose. Remember, the converter neck will be very hot. Once the converter has been removed, use a wire brush to clean the loose scale and rust from the outside of the exhaust pipe. Install the replacement converter onto the exhaust pipe. You may have to tap it into place with a rubber mallet. Use a block of wood between the converter and the mallet to prevent damage to the replacement converter. Install the new U-bolt over the converter neck at the rear U-joint about a 1/2 inch from the end of the neck, but leave it loose for the moment so adjustments can be made as necessary to align the flange holes at the opposite end. Position the converter so the flange on it is aligned with the flange on the manifold pipe. Push the bolts all the way through both halves of the flange and install the nuts. Tighten the nuts firmly and evenly. Now tighten the U-bolt firmly in place. On some vehicles, you may also have to replace the air tube leading down to the converter if it is rusted or damaged during the installation. Start the engine and check for leaks. Return the vehicle to the ground, and you're done.
Now let's review the procedures for identifying a plugged catalytic converter. There are 2 common methods used. For the first method, attach a vacuum gauge to a manifold vacuum source. Observe your reading at idle. Commonly, you will find that reading to be between 17 and 19 inches of vacuum. Now raise and hold the engine speed at 2,500 RPM. If the vacuum reading drops more than 3 inches of vacuum, there is a restriction in the exhaust. The other test requires you to drill an 1/8-inch hole in the exhaust pipe in front of the converter. Insert the vacuum gauge and note the pressure reading. With the engine idling, a reading of a 1/2 pound or less indicates a properly operating exhaust. If the reading is above a 1/2 pound of pressure, plug the first hole with an 1/8-inch aluminum rivet and drill another hole in the exhaust pipe after the converter. Once again, tap into this hole with the pressure gauge and note the reading. If the difference between your first reading and the second reading is over a half pound of pressure, the catalytic converter is plugged. Remember, safety first. Make sure you are always wearing eye protection and work gloves when performing exhaust system repairs. Always use jack stands to support the vehicle when working underneath it. Always allow sufficient time for the catalytic converter to cool before performing repairs. This can often take several hours. To replace a catalytic converter, first remove the flange nuts or bolts from the front end. Remove the old flange gasket if so equipped. Remove the clamp or hanger bolts securing the rear side of the converter. Separate the exhaust pipe with a hammer and chisel or by sawing it with a hacksaw. Clean the loose scale and rust from the exhaust pipe with a wire brush. Install the replacement converter on the exhaust pipe. Align the flange holes, insert a new gasket, and install the front mounting bolts. On some vehicles, you may have to replace the air tube leading to the converter. Tighten all clamps and hangers, and you're done.
Well, now that you've seen the tape, I hope you've learned as much as I have. As we keep learning more about the newer, more sophisticated systems, with the help from Champion Auto Stores, it becomes much less frightening to work on your own late model car. The tools are pretty much the same as always, but you do have to add a couple new things to your toolbox from time to time. One thing that's invaluable is the Haynes manual we've been talking about. Not just generic information, but specific photos and repair sequences about your particular model. You see, the folks at Haynes actually disassemble the entire vehicle they're writing about, photograph the process, and reassemble it. That way you're obtaining the most specific information available. And there's over 200 different titles. Visit your local Champion Auto Store to get one for your car. If you like this tape, keep watching for more Car Care Seminar videotapes to be released. They're all designed to help make you a more successful do-it-yourselfer. Until next time, I'm Bill Stern.